You going? Okay.
Yeah.
Okay. All right, so we did a different lab than previous groups. We did determining the concentration of a weak acid. So basically in this lab what we did is just another titration, except for this time it was mostly to figure out, do titration, figure out its concentration, and also at the same time, the first thing we had to do was to standardize NaOH, which is another process, another titration. Also in the lab, another one of the goals that you had was to understand the role of indicators in titrations, understand why we need them, and then also to continue practicing using balanced equations, because without them, any calculations that you do will be very difficult. And once you screw up a balanced equation, the rest of your lab starts to get more difficult.
Okay, so for the experimental, first thing we did was we had to create a 250 milliliter solution of 0.1 molar NaOH. Then we had to prepare the burette, and how we did that was you took the burette and you filled it with water, a couple times, and you had to go through and clean out the inside. And then you did the same thing except you used NaOH. Did that a couple times and filled it up, or kept it there and fill that up to 50 milliliters. And then we used the 100 milliliter solutions of KHP, which is the analyte, to help standardize the NaOH solution. And then we had to titrate an unknown acid that we were given with the standardized NaOH. So as far as standardizing the NaOH, we did 4 different titrations. We used the phenolphthalein as an indicator. And starting off, for an acidic solution, the phenolphthalein was clear, but as it became more basic, eventually you added 1 milliliter of the NaOH until you started seeing the pH rise to about 0.2 or higher, or until it started turning pink and then just fading away. Then you would reduce the amount by about 1 drop, or to about 1 or 2 drops, and you had to swirl it as you were putting the drops in, and eventually you had to reach kind of a fairly pink color. So not like super pink, kind of purple, but kind of like what's up there in the picture. And for as our data, we had the mass of each KHP we did. We started off with a rough trial, and then we had trial 1, trial 2, and trial 3. And those are the initial readings. That right here starting off, and finished with 16.28 milliliters used, and just gradually going down, starting off with 1650, ending with 33.85 milliliters. And then we refilled it to start off with 1.50 milliliters, and then finished with 19.85, and then again with 19.85, finished 37.51. But the important thing was to figure out the volume of NaOH used, which are the values on here. So roughly about 17 milliliters of NaOH was used per titration. And determining the concentration of the NaOH, we had the equation up there. We just used one calculation from one of our trials. We had the 0.3724 grams of the KHP, divided that by the total mass, and got 0.00182 moles of KHP. And because the equation up there, it's a 1-to-1 ratio, so as a result, it's the same exact amount of moles for the NaOH. Multiply that with the amount of NaOH used, which we had to convert that from milliliters to liters. So it's 0.01735 liters, and or 1 over 0.01735 liters. And we came out with then total molarity for NaOH is 0.105 moles per liter. And after about averaging them out or so, we got to about an average molarity of 1.03.
All right, and then you take that standardized NaOH, now that you know what the concentration of the NaOH is, you can then use it to titrate an acid. So here, basically the same sort of thing we were doing before. We use phenolphthalein as our indicator, so it's going to go from clear to pink. We did 4 titrations, so you would have one rough, so if you screwed it up, fine. You just use the other 3 and average them. So, like before where we had this very nice light pink over here, that's what you didn't want to get, really, really, really dark pink, because then you actually overshot the endpoint. You don't want that. So the same sort of process as before, except for this time we use 10 milliliters of the unknown acid instead of the KHP. And same sort of process, you take the initial and the final, and then you subtract them to the volume of NaOH, which you will then use in your calculations. That's the important number, along with the volume that you used of the unknown acid. Those are the 2 things that you needed. Make sure you knew them. You also had to know the volume of, or the concentration of the NaOH. Originally doing calculations. So this time, we already had balanced equation, so you knew what that was. This is good. So you just start doing stoichiometry, and what you're doing is basically ensuring that whatever you had on the top, you got rid of on the bottom, so that you would end up with moles per liter at the end. If you don't, then you need to redo your calculations because you forgot a step. So you just take the milliliters, convert them into liters, then you multiply it by the molarity of the NaOH, which you calculated previously, and then you do the conversion from your balanced equation into your moles of your acid, which in this case was acetic acid, and then divide that by your liters because you know how many moles over liters to get molarity, and then average your 3 different trials. Normally throwing out the one that is kind of way out there, which happens, just titration. You can do it over again. So some of the discussion questions here. The first one was talking about source of error. So if you had HCl in your KHP originally when you're standardizing the NaOH, they wanted to know what would happen. We said that the concentration of the NaOH would increase because there'd be less moles of KHP to react with the NaOH during the titration, but you'd still calculate the same number of moles being used because you didn't know the HCl was there. But the volume of NaOH actually that you actually used would decrease, so it's a fraction. And then the second discussion question talked about why we used KHP instead of just going with the mass that we found on the scale of the NaOH. The reason for that is that NaOH is hygroscopic, meaning that it absorbs water readily. So you really could never tell how much water was in your NaOH. The more humid it is, the more water it has, so you can't really, just by massing it out, determine how much water there was and how much NaOH there was. So that's why you have to use KHP to standardize it, because if you don't, then we would have just had 0.1 instead of 0.015, so then your calculations for the concentration of your acids would be thrown off. So you have to do that step with anything that's hygroscopic in order to make sure that you have accurate standardized concentrations when you're using titrations.
All right, so for the last discussion question, we had to figure out the molarity of the HCl, or the hydrochloric acid, right there with sodium carbonate. We have the equation up there, and after figuring out, we had 0.151 grams of sodium carbonate, and after doing some stoichiometry, which multiply that by 1 over the molar mass, and because it's a 2-to-1 ratio, as you can see, we have 2 moles of HCl to the 1 mole of sodium carbonate. You multiply that by the 2 moles over the 1 mole, and then from that you multiply that by 1 over the amount of HCl that you used, and thus we got the molarity of 0.1121 moles per liter of HCl. And in conclusion, after doing this experiment, we were able to standardize the NaOH that we had. And we used that to find the concentration of our unknown acid. And we ended up finding which we found the NaOH to be roughly 1.03 moles per liter. And the concentration of the unknown acid that we had was 812 moles per liter.
And then here are just our references where we got our pictures from and lab manual.